All right, welcome back. Let's look at rates of climb and how do we determine a thrust to weight ratio based on a wing loading for a climb requirement. Now there's two types of requirements we could have for climb. One could be for a best angle of climb, or an angle of climb requirement, climb gradient, perhaps. Usually gradients are used in specifications for certification. So I have this is from the back of the Raymer textbook. Let's look at this for a moment. This is looking at some FAR 25 requirements for multi-engine aircraft, and there are climb gradient requirements, which is the minimum climb gradient the aircraft must be able to maintain during different segments of takeoff, depending on the number of engines the aircraft has. So if the aircraft has one engine inoperable, it has to be able to maintain a certain amount of climb capability so that it can do a circle around maneuver and be able to land again safely. So this is if the aircraft is taking off, it exceeds that V1 speed in the balanced field length. And so if it were to start braking, if an engine goes out, it would run out of runway. So it's required, it has to take off. So it has to have enough power and thrust to be able to take off and climb to overcome that obstacle height and then be able to circle around and land with one engine out the whole time. So that's an example of a requirement that could be enforced by regulation. You might also have just a general climb requirement based on a desired performance of your aircraft. So perhaps you want your aircraft to have a time to climb requirement, just like in our project where we're following the AIAA individual challenge. The aircraft has to climb to 65,000 feet, and it has to do this within 1 hour. So we can estimate or get the average time to climb to get a rate of climb that we want in feet per minute, which ends up being just over around 1,000 feet per minute for this project. So let's look at climb requirements for best rate of climb and put in this requirement calculation. So our next column, if we look at our actual climb equation first, maybe that will help. So let's do that. Let me find our climb relationships. So this will be very similar to our cruise relationship, but from the Goodmanson and Raymer textbooks, just rearranging, solving our equations of motion for steady climb. So that means we're not accelerating. And some approximations, substituting in our velocity to maintain steady level flight, we can get this relationship here. So our thrust to weight ratio is equal to our vertical climb speed, our rate of climb, divided by our airspeed. So that'll be our forward airspeed. And we want to try to solve this for whatever airspeed is going to give us our best rate of climb. And that is going to be a function of our wing loading. And Raymer has a nice presentation of this equation, which I'll put on the screen in a moment. So we can get our V infinity, which is our best rate of climb airspeed. This is essentially when we take our relationship for the forward airspeed as a function of vertical airspeed, take the derivative with respect to our airspeed, set it to 0, we can maximize our rate of climb, and we end up with these terms: thrust to weight ratio and wing loading. And this is again based on the simplified drag model. So this term CD naught and CD min, that's just the same, just different notation between the two texts for the simplified drag model minimum drag on our drag polar for our 3D wing. So you can see we have our thrust to weight ratio equation in terms of some airspeeds, our dynamic pressure, which is calculated at this airspeed V, wing loading, minimum drag coefficient, our lift-induced drag coefficient, K, which again is 1 divided by pi times aspect ratio times our span efficiency, divided by Q, which is our dynamic pressure times our wing loading. So we're going to have this interesting function, and our best airspeed, or airspeed that gives us our best rate of climb, is also a function of wing loading and thrust to weight. So we're going to have a recursive function, or a function that's a function of itself. So Excel doesn't like that. Let's just program it in anyway, and then see what we have to do to make that work better. So what I'm going to do now for our best rate of climb is I'm going to plot 3 columns. The first column is going to be our best climb speed, and the next column is going to be our dynamic pressure Q based on our best climb speed, and then our third column is going to be our thrust to weight ratio based on this top equation here. So I'll leave these equations here for us to reference. But the first one, I'm going to have best climb, I'm going to say best rate, best climb speed. I'm going to put it below best climb speed. And this is, the notation for this is V epsilon, or V upsilon. So I wonder if I can do that. Vy, epsilon looks like a Y with this keyboard, I guess. So V sub Y, this is the notation for our best climb airspeed. And I'm going to calculate this in feet per second. I want to make sure I have the correct units. So we have our best climb speed. Let's make these bold. The next column I said is going to be our dynamic pressure. So dynamic pressure, and that is Q. And that's going to be pounds per square foot. And it's going to be at sea level conditions. So I'm just going to write sea level. Center these. And then our third column is going to be our rate of climb that we want, which is also sometimes just written as ROC. And this is going to be our thrust to weight. And that's going to be in our sea level condition. So when we're plotting our climb, just to separate these out, helps with troubleshooting if we make a mistake. So these 3 are going to be bundled together as one package. So first of all, let's find our best climb speed, and we'll use this equation down here. So this is going to be equal to the square root of our wing loading divided by 3. Again, I'll put it in brackets. If you don't want to use brackets and it's just too tedious to write that many brackets, everything that's in the denominator just keep dividing by. So it treats it as a separate division. It's not now 3 divided by something. It's imagine multiplying by 1 over the value. So 3 divided by our density at sea level. Scroll up, find our density at sea level. Come back down, divided by our minimum drag. So our minimum drag, again, we estimated that as 0.025. And then we have all of this times, in brackets, our thrust to weight ratio. We don't have a value for thrust to weight ratio yet. This might be a problem when the equation gets in front of this, so I might have to remember H51 and type that in. So thrust to weight ratio plus, we have the square root again, square root of our thrust to weight ratio squared plus 12 times our minimum drag up here times our lift-induced drag coefficient. So I have that calculated over here, 0.04207. So I'm going to have a closed bracket to close off the square root, the small square root, another closed bracket for the next one, and another closed bracket for the large square root. So the answer it should give me is not going to be correct because it's assuming thrust to weight ratio is 0. So it's just going to be the square root of our minimum drag term times our wing loading and so on. Next, we got to find our dynamic pressure. Dynamic pressure is equal to 1/2 rho v squared. So 0.5 times our density at sea level. Scroll back up. way up here, times our velocity. Now our velocity is already in feet per second, so I don't have to worry about multiplying by 1.688, which is nice. So our velocity squared, and that gives us our density, our dynamic pressure, rather, and then lastly we have our rate of climb equation. So our thrust to weight ratio is equal to our vertical climb rate, which is our coming from our requirements. So we might have a rate of climb. Where is our requirement? See if we can find it. So our rate of climb here coming from our RFP, I estimated that as 1100 feet per minute. So we need to convert this to feet per second so it's compatible with our forward airspeed units. To go from feet per minute to go to feet per second, we just divide by 60. You think you're not traveling as far in 60 or 1 second as you are in 1 minute, so it should be a smaller number. So this number divided by 60 divided by our best rate of climb airspeed, which is over here. That's our aircraft forward airspeed, plus our dynamic pressure divided by our wing loading times our minimum drag, CD min, plus our span efficiency, or sorry, our induced drag coefficient divided by our dynamic pressure times our wing loading again. So it's nice having those two columns in there. I can make this last function much simpler. And I already have my Excel set to show iterative calculation. So it didn't give me any errors here. Let me show you what it looks like if you don't have this turned on. So if you go to your settings, this is what it looks like for a Mac. Go to General. Go to Formulas and Lists, and go to Calculation. And then what I've done here is I said use iterative calculation. I'm going to turn that off, and you'll see what happens. There are one or more circular references. So that means one function is a function of another cell, which then depends on that original cell. So it shows up, if I edit this, let me add our dollar signs and see if it still gives me this error. We want all of these terms to be constant. Let's fix these ones. There. So now we have some issue appearing. So again, I'll just change all these, and I'll show you how to get rid of this issue. So we just want to keep anything that's in got the number 51 at the end. Good. So this is a circular reference. That means this function is a function of this number, and this number is a function of this number. So Excel doesn't like that. So what we can do is turn on iterative or allow iterative calculations, which means it will, based on an initial guess, continue to go through this until it converges on a value, and we can control how many times it calculates before it comes to a convergence, and we can control what that convergence tolerance is. So we'll go back in here, use iterative calculation. The default, I believe, is 100 iterations, which might have been a lot if you were using Windows 95 or Windows 98. You can set this a bit higher. 200 is probably enough, maybe 250. And then you can adjust your maximum change. So if the change is more than this, it'll keep iterating. If it's less than this, the iterations will stop. So if it converges to smaller value than this change after one cycle or one iteration before it reaches the 200 iterations max, then it will just stop. So I'm going to leave it like this. And as soon as I exit out of this, we should see it there. It starts to calculate. It shows it's a circular reference. But the problem goes away. So now if I copy this down, just make sure it's using the right values. Good. And I copy these down so I can highlight both. Move these out of the way. We can get our rate of climb, and now we're actually calculating our thrust to weight ratio based on the best rate of climb at that thrust to weight ratio and at that wing loading. So we get a pretty good estimate And when we plot this, it gives us an interesting result. So let's add this data to our plot. So I'm going to add this as rate of climb, ROC requirement. And again, this is at sea level. So maybe we want to add one at altitude, or we can look at the effect at altitude just by changing the density parameter, or we can just copy that over. So now add our Y values, it's our thrust to weight ratio that we care about. I'm just going to add here sea level, so I know. And we scroll up, and then we have this plot. So that's this curve right here that just showed up for our rate of climb. So our rate of climb, if we have very low wing loadings, we need a lot of thrust to generate the same rate of climb. So that tends to be a minimum somewhere over here. And actually, if we were to change this plot and allow it to show further, we can get a better sense of how that changes with increasing wing loading. So if we have an increased wing loading, we can have a better reduced engine requirements for our rate of climb. And that's just for several reasons, or a couple of reasons. But what we're looking at here is, trying to fine tune and figure out where is this optimal point going to be. So as we keep adding these constraints, it looks more and more like, based on the parameters for our aircraft, this fictitious aircraft, I just chose numbers out of a hat. We have a wing loading of around 25, and we could get away with all these requirements with a thrust to weight ratio of, maybe 0.18, which is quite low. So maybe our requirements are a little lax, or we're overestimating the capability and the coefficients for our aircraft. So who knows? So let's add this again and look at the effect of our rate of climb at altitude. So I'm going to change, as we increase our altitude, density, the air is thinner, our rate of climb is going to decrease. Eventually the air is too thin, you can't climb anymore, and we reach our absolute service ceiling. So you can add a service ceiling requirement, which basically sets, my best rate of climb, or my rate of climb, I want it to be 0. Or if you want your service ceiling, that's by definition when your rate of climb reduces to 100 feet per minute or less. So if you set your rate of climb to 100, then you have the requirement for your service ceiling by then solving what that density would be at whatever altitude given a thrust to weight ratio. That would usually come in more so with performance, unless you have a service ceiling requirement for your aircraft. This aircraft has a pretty high rate of climb requirement. I think the cruise condition at 65,000 feet may be driving that, as well as this rate of climb requirement given the weight of the aircraft. So let's do that then quickly. Let's plot. I'm going to copy these over, and we're going to plot these for sea level conditions. Now maybe what I should do before doing this, let me undo that move. I'm going to take all of the values that I don't want to translate by column, and I'm going to add $ signs in front of the column values. So H is fine, D and D. Next one is a little simpler. And then the last, leave F. G, all we want to keep is A. So we want to use still as a function of our wing loading. All right. This shouldn't change our formulas. I'll copy those down though, just so Excel doesn't bother me. Copy those over, good, we still have some values. So now what I'm going to do is change the density value in this equation to match the density at altitude. So we found that in our atmospheric modeling. So I'm going to delete this, and let's go over to our atmospheric model, somewhere up here. And let's say we are interested in knowing what is our rate of climb, or our density rather, which is this column here. And I want to know what that is at, let's say 30,000 feet. So what's our rate of climb at 30,000 feet? So that's 16, and I want to go over to column Y, so Y16. Found a typo, tried to correct. Sure. I corrected it wrong. I'll just put this in here, Y16. And I want this to be fixed. Now, because it's an invalid number, there's an error somewhere, of course. It's giving me this issue. So let's just make sure all these values are correct. We have all of our values here are okay. And look, it sorted itself out. And do we have density values in here? I believe we do. So this D8, we got to change to Y16 then. And that's going to give us our density at that 30,000 feet. So let me just double check for my own sanity. I'm going to move this out of the way. Y16 is right here, Y and 16, so that gives us our density of air at 30,000 feet. So this is now finding the same thing as before. What is the thrust to weight ratio based on a wing loading that we need to maintain 1,100 feet per minute climb rate at 30,000 feet altitude? So take those values, copy them down, and we're going to add this. I'm going to select data. Now we're going to add rate of climb. And flight level 300 is 30,000 feet. We have our X column, our wing loading, and our Y column, our thrust to weight ratio. So we can see if we want to maintain that climb rate at 30,000 feet now, we have to have more thrust for a given wing loading. So if our wing loading is still at 24, 25, we need to have a higher thrust to weight ratio in order to meet that. Oh, sorry, a lower thrust to weight ratio. It went down to maintain that. So if we increase our altitude, our thrust to weight ratio requirement decreases. So you can plot this for altitudes of interest and different kinds of conditions, different aerodynamic values. You can play around with your CD min, play around with your aspect ratio, and see how that affects your constraint analysis. And as we add more and more points, we're trying to refine out what is going to be our optimal thrust to weight ratio and wing loading. Right now, based on the values we've chosen, it looks like we're going to have 25 wing loading roughly and about 0.18. So you might be asking, why is our rate of climb a more relaxed requirement at higher altitude? Well, if we compare some things, let's look at our airspeeds. Our best rate of climb airspeed at sea level, the same wing loading of 12, 167.7, whereas at altitude we're going 245.9 feet per second. So because we can carry a higher climb forward airspeed, we can generate more lift and we can get more climb, plus we're traveling faster. So even if our climb gradient is less with a lower thrust to weight ratio, because we're traveling so much faster, we actually have a higher climb rate. So that's what's largely contributing to this, and it's all based on, or because of that best climb rate equation. So in our next video, we'll look at cruise and landing, and then that will pretty much complete our constraint diagram for some of the basic requirements for an aircraft.